Jai Hind students, today we are going to cover a very special topic, that is canonical cover. In this lecture you will be able to understand what is the canonical cover. It is also known as minimal cover, and what is the definition of it and how we can calculate the canonical cover if the functional dependency set is given to you. We will take some example also. We need to understand first what do you mean by the extraneous attributes. Extraneous attributes are nothing but the attribute of a function dependency that can be removed without changing the closure of the set of the function dependencies. Now, we will understand what is the canonical cover. A canonical cover, that is also represented by FC, of a set of functional dependencies, that is known as F, such that all the following properties are satisfied. So, what are these properties? F, it should be logically implies all dependencies should be in canonical cover, that is FC. FC, that is minimal cover, logically implies that all dependencies in that given set F. Third condition, no functional dependency in minimal set contain an extraneous attribute. So, we need to remove all the extraneous attributes, right. Each left side of the function dependency in canonical cover should be unique. It means what? If we are having two function dependency set, alpha 1 tends to beta 1 and alpha 2 tends to beta 2, such that alpha 1 tends to alpha 2. It should not be there, right. So, this is about the definition. Now, the important thing is how to calculate. So, we will discuss by two examples. So, I am taking one example to discuss how, if a functional dependency set is given to us, how we will calculate the canonical cover or minimal cover from that. Okay. So, here one example is given, a relational schema R having 4 attributes A, B, C, D, and a functional dependency set where 1, 2, 3 functional dependencies are given to us. Now, we need to find out the canonical cover. Okay. So, the first step is we need to decompose the functional dependencies using decomposition rule. Decomposition rule we have already studied during the Armstrong axioms, right. So, we will decompose each and every. So, here in the first functional dependency set, no need to decompose as the right hand side only one attribute is there. But here if we see this AD tends to BC, so B and C, two attributes are there at the right hand side. So, we need to decompose it. So, after decomposition we will get these two functional dependencies, right. Okay. So, further the next functional dependency C tends to ABD. Here we can see there are 3 attributes at the right hand side. So, we need to decompose these functional dependency in these 3 functional dependency. So, this is by the decomposition rule. The next step is to find a closure of the left side of each of the functional dependency by including that functional dependency and excluding that functional dependency. So, we need to find out the closure of each of the left hand side by using one functional dependency. Once we will include it, and in the other step we will exclude that functional dependency, and in both cases if the closure is same, then the functional dependency is redundant and we can remove that functional dependency from the given set. Otherwise, if the closure are different, then we need not to exclude that functional dependency. This is what the rule. So, what we will do? We will find out the closure of the left side of the given functional dependency. Once we will include it, and second time we will exclude it. If both are same, it means there is no need of that function dependency, we can remove it, because without using that function dependency we are getting the same closure, using that function dependency we are getting the same closure, it means no need of that. And if both are different, it means what? If we are having that function dependency, we will have different closure. if we are not having that function dependency, we are having different closure. It means that function dependency is very, very important. We cannot exclude it, right? So this is very important to know. Now, we will calculate the closure of all functional dependencies one by one. So first, in the first step, 1a, we will find out the closure of this. So closure of this b plus, using all the functional dependency set, and in the step b, a, b, we will find out the closure of b again without this functional dependency set, after removing this functional dependency set. Yes, in this we are having this, in this we are not having this, b tends to a. So we will see, if we are getting the closure, it means b we are already having. If we are having b, we can reduce a, but after a we are not able to reduce anymore. So closure of b is ba here, using this functional dependency set. Here if we are calculating the closure of b, so we are having already b and we have removed this function dependency. So if we are having b, we will not be able to calculate, we will not able to find out another attribute. It means what? Closure is only b. So what we have seen here, ba, b. So closure is different during both the calculation. So from from a1 and b1b, we find out that both the closure, including this and excluding this, are not equivalent. So the function dependency b tends to a is important and it cannot be removed from the set of the function dependency. Understand? Okay. Now what we will do, we will calculate the closure of this ad, right, using this function dependency and without using this function dependency. So in the 2a step, we are calculating the closure of ad, that is known as ad plus. So with these function dependencies set. Okay. So here we can see, if we are having ad, what we can calculate? B. What we can have? B. We can find out the b. So now ADB is the set. If we are having ADB, what we can reduce? We are having B, we can get A. So what is the closure now? ADBC. Now we are not able to reduce anything because we are having only 4 attributes in the relation. So we get all the attributes in this. So ADBC is the closure using this function dependency set. Now we will calculate the closure of AD without using this functional dependency, means excluding this function dependency, only the set of this, right. So AD we are already having, right. Now if we are having AD, we can reduce C. So we can get the set ADC. Now if we are having ADC, we can reduce A, B, A is already in this, B we can reduce B, so we can add this B here and D is already here. So we can reduce all A, D, B, C, B all. So here we can see we are calculating the closure of AD using this functional dependency, without using this functional dependency, but in the both cases closure is same. It means what? We can reduce that this functional dependency is not useful. Without that functional dependency also we are getting the same closure. So what we can do, we can remove it, right. So now the new functional dependency set after removing this is what? B tends to A, AD tends to C, C tends to A, and C tends to B, C tends to D. So this is our minimized set. Not properly minimized, we need to follow further steps also. Okay. So next, in the next step, we will calculate the AD plus again for this functional dependency. Now we are working on this functional dependency. One by one we need to work on each and every functional dependency. So now we will have a closure of this with having this functional dependency, without having this functional dependency. Okay, so here we are already having AD as given, and if we are having AD, we can deduce C. So we are having ADC. If we are having ADC, we can deduce B also. So we get this. Okay. Now we need to calculate the closure of AD without this functional dependency. It means this set. Okay. So we are having AD, right? So if we are having AD here, we can see what we can deduce. Nothing. Nothing can be deduced because not a single functional dependency which is starting with the AD, right? So we can get only AD, not more than that, any of the attribute. So here we can see that this closure set and this closure set both are not equivalent. It means what? This functional dependency is important. We cannot leave that. We cannot remove from the set of the functional dependency. So hence the resultant set remaining the same, right? Now we will work for this functional dependency in the next step. So one by one, what we are doing, we are working for each and every functional dependency, and we are finding out the closure of the left hand side. So here we can see left hand side is what? C. So what we will do next, we will find out the closure of C. So the closure of C having all the functional dependencies set is, we are having C. Okay, so if we are having C, we can get A. If we are having C, we can get B. So A, B, C. Now we are having A, B, C. If we are having C, we can get D. So what is this? We can get A, B, C, D. Yes, it is written here. Okay, now we will calculate the closure of this C again without using this functional dependency. So the set is without that functional dependency is this. Now what we are having in our hand? C. If we are having C, what we can reduce? We can reduce B, D. Okay, so we are having C, so we can reduce B, we can reduce D. Now if we are having B, we can reduce A. So again we are getting C, B, D, A. So here we can see both are same. So if we are calculating the closure without this functional dependency and with this functional dependency, both closures are same. It means what? What we can deduce? It means this functional dependency is not important and we can remove it from the set of the functional dependency. Right. So after removing that particular functional dependency, if we are removing this, we are having B tends to A, AD tends to C, C tends to B, C tends to D. Now we are having these four functional dependency with us. Now we need to work on the next functional dependency, that is C tends to B. Right. Okay. Now the next step, we need to calculate the closure of C again using this functional dependency set and without using this functional dependency set. So after removing, we are getting this. Okay. Now what we are having in our hand? We are having in our hand C. If we are having C, what we can deduce? We can find out this B. So we can have CB as a closure. Now if we are having C, we can deduce D also. So we can have this. If we are having C, B, D, what we can deduce? If we are having B, we can deduce A. So now C, B, D, A in our hand with this functional dependency. So in that case, closure is C, B, D, A. Right. Now we will calculate the closure of C again without this functional dependency, means from this set only three functional dependency we are considering here. So C is we are having, if we are having C from these three functional dependency, what we can reduce? C I am having, D I can find out from C, but after that if we want to get this A, we require B, but we are not having it. So what we are having here, as a closure of C, we are having CD only. So when we are taking the closure with this function dependency, we are getting C, B, D, A. But when we are taking the closure of C without having this functional dependency, we are getting only CD. It means what? We can find out that functional dependency C tends to B is important and we cannot remove it from the set of the function dependency. Hope you understand where we will be able to remove that functional dependency and where we need not to remove that functional dependency now, right? So we cannot remove this function dependency, so set remain same. We need to consider all 4 function dependency for the further step. Now only one function dependency is remaining here, that is C tends to D. Now we need to find out the closure of C again using this function dependency and without using this function dependency. So in the step 6 we are having 2 steps. 6a means what? We need to calculate the closure of C using these 4 function dependency and we need to find the closure of C without using this functional dependency, right? So if we are using this function dependency set, we are having C in our hand. If we are having C, we can reduce B. If we are having C, we can reduce D. So we can get this. And if we are having, now we are having B with us, so we can have A also. So now this set is CDBA. Fine. Okay. But if we are not considering this functional dependency, we are having only 3 functional dependency. Now we will calculate the closure. We are having C. If we are having C, we can reduce B. Okay. If we are having C and B both, we can reduce A also. But anyhow, we will not be able to reduce this D. So what we are getting here? CBA. So we can find out the closure of C is different from closure of C when we are considering this function dependency and we are not considering this function dependency. It means closure is not equivalent. So this functional dependency C tends to D is important and we cannot remove it from the set of the functional dependency, right? So now again, what I am getting the reduced set that is having all 4 functional dependency. Now we have considered each and every function dependency, so we cannot reduce more on the basis of this. Now we need to consider one more step. Okay, so the next step is what? We need to check, this is what the resultant functional dependency, right? Now we need to check the redundancy of attribute. Where we can get this? We can have, we can look at this functional dependency here. AD tends to C is there. So we are having A and D 2 attributes at the left and the side. So we need to check that both are important or only one will be sufficient, right? So what we will do? We'll do again the similar kind of step. So what we will do? We will find out the closure of this AD. So AD plus, we will calculate the closure using this functional dependency, right? Using this functional dependency, and we will find out the closure of only A using this functional dependency, and we will find out the closure of D using this functional dependency, right? So what we are doing? We are basically checking the redundancy of attribute. Here we can see A and D, 2 attributes are there at the left hand side. So we will need to check that both are important or only one will be sufficient. For that we need to check the closure of AD, A and D separately. If it will same AD or A, both closure will be same, it means what? A will be sufficient. So we need to check here. Okay. So if we are checking AD, closure of AD, so we are having AD in our hand. So we can get the C. If we are getting C, we can get the B. So all attributes can be find out if we are having AD. But if we are considering only this A, So we'll have A in our hand. So only if we are having only A, we will not be able to deduce any attribute. So the closure of A is A only. Now we'll consider D. So if we are having D in our hand, what we will able to find out? Nothing. So we'll have D in our hand. It means what? There is no redundancy. A and D both are important. Only A or only D will not work out, right? So we cannot remove any of the attribute. Both A and D are important attribute. So what is the canonical cover? Canonical cover is basically this, but we can rewrite as we have decomposed the first step. Now what we will do, we will unite. Okay, what we will unite, we will see that because this is the condition that alpha 1 tends to alpha 2 should not be there in two function dependency, where here we can see that these are same. So what we need to have union of those. So B tends to A will remain same, AD tends to C will remain same, but we will apply this union on these two function dependencies. What will happen? C tends to BD. C tends to BD. After union, we can get that. Okay. C tends to BD. Okay. So what this is the canonical cover of the given function dependency. Initially, we have given this function dependency. This is what the FC. This is the canonical cover. Hope you have understood this. We can take one more example to make better understanding, or for the revision work, how we can calculate the function canonical cover from the given function dependency set. Let's suppose we have given the relational schema in which 4 attributes W, X, Y, Z are given, and these are the function dependency set is given. So the first step, we'll revise thoroughly. Okay. So now what is the first step? Decomposition, using the decomposition rule, and decomposition held on the right hand side only. So here we are having the left hand side same attributes, but right hand side we have decomposed. So this one we have decomposed in 3 functional dependencies only. Okay, so these 3 functional dependencies instead of this one are here. So first step is the decomposition. Next step, we need to find out the closure of each and every left hand side attribute or combination of the attribute without using that function dependency with using that function dependency. That is the next step that will go on for each and every functional dependency, right? So then the first step, 1A and 1B, what we are doing, we are considering this functional dependency and calculating the closure of W, right, without using this and with using this and without using this. So we can quickly look here, both are not same. It means what? We have discussed previously also that this function dependency is important and we cannot remove it. So the set will remain same. Now we'll consider the next functional dependency, Y tends to X. What we will find out? The closure of Y using this function dependency and without using this function dependency. So we can see here both are different. It means what? This also cannot be removed. So the set will remain same. Okay. Now in the next step, we'll consider this functional dependency and we will find out the closure of Z. So the closure of Z using this function dependency is this, and without using function dependency is this. It means what? This functional dependency is also important and when we cannot remove it, the set will remain same. We are not able to reduce till now. Next considered function dependency is the Z tends to X. So here if we are calculating without using this with using this function dependency and without using this function dependency, the closure is same. It means what? We can remove it. It is not important. So the first function dependency we are able to remove it z tends to x. So the now resultant set after removing this function dependency is this we are getting. Okay. Now the next step we are doing for this function dependency. The same steps we are doing this function dependency, we are calculating the closure of z. So in both steps, closure of z is different. It means this functional dependency is important. So the resultant set is this. Now we will consider this functional dependency and we will find out the closure of wy. Using this functional dependency and without using this functional dependency, we can see both are different. It means we will not remove it. It is important. So at last we can see that we are able to remove only one functional dependency in whole steps. Now the last step is we need to check w and y both are important in this function dependency or some can be removed. Okay. So in the last step we'll check with the closure of wy, w and y, right? Okay. So we'll check. So here we can see different. It means both are important. So both attributes are important. We cannot remove any. So the functional dependency set, which is the minimal set, is this, and after union we can write this set as the functional dependency set, and it is the canonical cover of the given functional dependency. This was given to us, right? So hope you have understood how to calculate the canonical cover. It is very important topic. So here I am leaving, and in the next topic we'll take in the next lecture. Thank you so much.